is Thomas Kim. In this session of video, I am going to explain how to implement extended Euclidean algorithm. Before I explain extended Euclidean algorithm, I will let you know the background theory, why we need to solve extended Euclidean algorithm. Suppose we are going to solve 17x 3 mod 29, for example. If we are going to solve this equation, we need to have a multiplicative inverse of 17. We need such number 17 inverse times 17 modulo 1 mod 29. If we can find such number, multiplicative inverse, multiplicative inverse, we can solve this equation. For example, if we found this number 17, inverse of 17 is, for example, 12 mod 29. If we can find such number, this is multiplicative inverse, we can solve this equation. So how to find this number, multiplicative inverse, is the key of this problem. So if we can find this multiplicative inverse, this is 17 inverse, we can multiply each side, then it becomes 17 inverse times 17 x, then we 12 times 3 mod 29, then we have this equation 17 inverse to apply both sides, this one, this to this, then we have this equation. Then this is identity 1, so leaving x, then it becomes 36 mod 29. So this side we apply this one again, then the remainder would be, the remainder is 7. So then we solved the problem like this. So the key is how we going to find this number. How we going to find how we get multiplicative inverse. So to understand this, let's rewrite this equation. Suppose, okay, I will rewrite it. 17 inverse 17 modulo 1 mod 29. Since we don't know this number yet, I will let it as, then 17 modulo 1 mod 29. Since we can write for any number t, we can write any number t, 29 is modulo 0 for mod 29. We can write it like this. For any number t, 29t would be 0 for mod 29. If we plus them, then it becomes 17s plus 29t equal 1 mod 29. So in this equation, I will write this equation here once again. (17s plus 29t 1 mod 29. in this equation, please note that this term can be 0 because this is 29, this is 29. This term can be 0, always can satisfy here, can satisfy. If this term becomes 0, S actually means multiplicative inverse of 17 mod 29. So this S actually means 17 inverse. What this number would be. So if we can solve here, we solved 12. This is the if we can find this multiplicative of inverse, we can solve such kind of problem. So in this session of video, extended Euclidean algorithm actually solves this equation. Because if we can find S and T, then we can solve problems like this. For example, if we can find S plus 29 T, this side does not need to be mod 29. This can be GCD. This is greatest common divisor of 17 and 29. If we can solve this problem, especially the GCD of 17 and 29 is 1, then it becomes like this. Then if we can solve this problem, equation about S and T, then we can solve problems like this. 17x k mod 29 or 29x mod k mod 17. We can solve such kind of problem if we can solve this equation. How to solve this equation is extended Euclidean algorithm. I will recommend you a few YouTube video to watch. Then I will explain how to solve this algorithm. I will resume this video after giving you some advice, some tips, watching YouTube videos about the theory. If you haven't watched my Euclidean algorithm, if you don't know what Euclidean algorithm, please watch my video, and you can watch the video here. Also, I will explain extended Euclidean algorithm based on this man's video, John Bohr's video. My algorithm is implemented based on extended Euclidean algorithm example by John Bohr, this website, this video, YouTube video. And also I recommend you watch this video, extended Euclidean algorithm inverse modulo tutorial by Emily Jane. And also I recommend solve linear congruence using Euclid algorithm by Math with J. These all four videos are very useful, especially about Euclidean algorithm theory and implementation. My video can be a lot helpful. After watching this video, please watch my explanation how to implement extended Euclidean algorithm. We are going to solve ax plus by equals GCD. Here x and y. This is Euclidean algorithm. If you have watched the video I recommended, you will understand. You will have no problem following with me. So basically we are solving such equations. 56x plus 15y equal GCD 56 15. This is actually 1. So in this equation, 15 is here. This is initially A, this is A, this is B, A, this is B, and this is quotient. This value would be, this value is 3, and this is calculated like this. A, B over A, is this value, and this value 11 is remainder A modulo B, this value remainder. So the value would be 1, 2, 1. So you understand the concept, right? I will call it quotient. I will label it Q0, for example. This one Q1, this is Q2, this is Q3. If we label it from this is original equations, we move it like this side, then it becomes this way. Then from minus, I will change it minus, then I will put like this, plus, minus, plus, minus, plus, minus, like this. Then this is the result equation here. So this, I left this will be Q0, Q1, Q2, Q3, like this. Then this Q0, Q1, Q2, Q3. So at this point the calculation ended. We are going to make some equations from here to make to C++ code. This is the first step. We should think here is number 1, for example. I will label it like this: X bar plus Y 3 bar, and this side is does not important. So I will let like this. This is the first step. Here, number 1 is X is equal 1, and here Y is Q3, Y equals Q3. This is the first step, the first equation, for example. Then we are going to say we have to replace this 3 here, this equation. So if we let it this like this, we are going to solve it. X bar underscore plus Y. Instead of 3 underbar, we are putting this equation here. So it becomes 11 bar plus 4 bar Q2, like this. So we have to solve it. I will expand it. X bar plus Y 11 bar plus 4 bar Y Q2, like this. Now compare this equation with this one. This is the next one. So we will put 4 bar here. So 4 bar should come on the right hand side. So with plus, I will collect only 4 bar part. This part. Then it will be like this. 4 bar. I would say 4 bar, X plus Y Q2. This is 4 bar. Then on left hand side, Y 11 bar. Like this. Compare this one with this one. 11 bar, 4 bar. So this equation and this equation matches. The reason I have to put this way is we are going to put this one here. So it should be on right hand side. If we compare this one with this one again, this is the first, this is the next. If we compare it, the next X, this is X prime. This X prime, Y bar, 11 bar, plus this is Y prime, the next 4 bar, like this equation. So X prime will be this one, here. This will be assigned to here. So we have to save t. We have to save this here x. This is x, right? So we have to save x. We save previous x here t. T is temporary actually, temporary variable. We save the variable x at t, and then x will be, this is x bar, x prime will be y. Okay, y will be saved to here, will be assigned here. Then y should be this equation, x plus y g2, not g2, q2. So this y and this y is different. This y is actually this one, right? So the previous one, this one. So this with these two equations, this is the initial step. I will summarize here. I will summarize here. Initially x equals 1, y equals q3, the last one, q3, and the next loop, t equals x, we save t temporary place, then x would be y, the previous y comes to new x, and new y will be x plus y times q2. So if it is called, okay, this is the way, the first step q3, q2. So if we have to remember this relationship, Now here I have to mention another thing. Here q is actually minus here. This is q, initially q. So we have to define q0 like minus 3. So it should be here q0. It should be like this, minus a b over a. A divided by b. So here we say q would be a divided by b minus. Okay. So I will delete all, and I will give you C++ code now. I will arrange once again. This is A, this is B, and Q are computed like this. QI would be computed minus A, B over A, and initially X will be 1, and Y will be Q, the last element, Q last, I would say last. Then at the second step, it will be recursively called, it will be called repeatedly. Secondly, we will save tx to a temporary place. Then x will be y, the previous y will be assigned, Then uy will be x plus y times q, the previous one, q p r e b, like this. This is the algorithm. Now first I will make it using loop. Explaining using loop is actually easier, but I will also make code using recursive code as well. First I will explain in loop. So the first thing, using loop solution. Now we are going to get GCD, int GCD. Here we will call A, B, X, Y. A, B, X, Y. This is Gaussian Euclidean algorithm. So I will explain Euclidean algorithm, then I will expand to extended Euclidean algorithm. In Euclidean algorithm, we learned something like this. If B greater than A, this step is actually important. B greater than A, we swap AB. Then we let int R, we declare R, Y, R equals, we get remainder, A, remainder B, A modulo B, remainder is not zero. Remainder is not zero. We are doing recursive, we are doing loop. Here, we say A would be B, we say B previous B, and B equals R. At this step, after loop, return. When R is 0, A modulo B becomes 0, remainder becomes 0, that remainder B becomes GCD. Okay, this is our Euclidean algorithm. Now I'm going to expand it to include this equation. Okay. To expand it, I'm going to okay, I will erase this part and I will declare some more variables. So int Q, I will say int R, count, I will initialize count 0, then also int Q, I will say 100, for example. 100 integers, I added these two items now. Now, while R equals A modulo B remainder. I don't need this. Is not 0. Then here we set QI like this. Please remember. So we let Q count. Then we increase like this. Then we let A over B. Please remember this minus symbol like this. Then the remainder is the same as we have done before. A equals B, B equals R. Okay. At this point, I would say int G equals B. This is GCD actually. I would say GCD. It will be returned GCD equals B. This is actually return value GCD, greatest common divisor. Then here this is the initial step. Okay, say if at this point if count. Okay, say count actually means how many times this loop executed. If count is 0, if count is 0 means it never executed this loop. Count equals 0. Let's see what it means. Okay, let's see what it means. We are solving this equation. For example, 15 times 15 x plus 5y equals, for example, GCD would be 5. If we are solving this equation, okay, this is A, this is B, 15 modulo 5, 0. Okay, here A, B is B5 is GCD. In this case, the count, this loop will not be executed. It jumps at this point. Count will be 0 because here 15 modulo 5 will be 0. Okay, so this loop never executes. In such case, if it is going to, this equation is going to be true, then it should be 0, and y should be 1, right? So here we let x equals 0, y equals 1, then return GCD. Actually, we don't need this. We can just say B, return B. Then it ends. Okay, so I will move it up like this. If count equals 0, then x will be 0, y would be 1, then return B. B is GCD. So the equation ends. Now count is greater than 0 or not equal to 0, then else. Okay, this block executes. I will use this space. Then in else statement, if else statement here, initially we let x equals 1. Here initially x equals 1, y equals q last, the last element of q array, the last element count actually decodes, right? So y should be q count. Here should note that count is plus after assignment, then when it loops out it's plus 1, so it should be minus 1. It should be q count minus 1, like this. This is initial stage. Now we are going loop. We are going to compute this now here. Now it continues. If we will use for loop, it should be int. You should not use size. Okay, so int I will be it. If it is 3, for example, when in our example it was 3, it was 2. At this point, count becomes 4. So 4 minus 1 becomes, this is Q3, the last element. So we have to start count minus 2. Minus 2 is important because count will be 4, minus 1 will be 3. This will be Q3, and this will be Q2. So it was minus 1. Then I should be greater than or equal to 0. See, if we are dealing with 0, it should not be size int. Unsigned. You should not use unsigned here. If you use unsigned, this does not hold. So then we are decreasing minus I. We are decreasing I here at this point. Now we are applying this int t equals x, y equals x, we are executing this step. No, sorry. X equals y, then y equals x plus y times q. Here, count I, index I. Then after this loop, every processing is done. So we return. Here, return. What should we return? GCD. GCD value would be B. Here, GCD would be B. So return B. Then our program ends. This is the way loop. I can do it with using loop. So loop is actually much faster. It's about, I tried with loop and recursive function call. It's about 30%, 130% faster. About 1.3 times. 1.3 times faster. I'm sorry, I made a simple mistake, but very important. So the initial condition is correct. X equal 1, y equal q3, or the last element of q, the last one. But in loop, it should be like int x would be y. Then I made mistake here. Y should be t plus y times q2. Q, the previous one. So I have to fix like this in all subsequent videos. So I made mistake like this. I have to fix like this. Please fix like this when you implement the code. I'm sorry. Now I explained the same thing using recursive function call. Using recursive function call, it will be something like this: int gcd int a int b int x int y. Here first we calculate r. int r equals a modulo b. Please note the precondition a should be greater than b. Precondition a should be greater than b. Greater than or equal to b. Okay, this is precondition. We will not do swapping. Then if r equals 0, if r becomes equal to 0, r becomes equal to 0 means, as I explained before, 15x plus 5y equals 5, GCD 5. In this case, 15 modulo 5 is 0, right? The remainder 0. So the remainder 0, it means x equals 0, y equals 1. Okay? So you have to remember x equals 0, y equals 1, then return b. B is the remainder, the GCD, so return b. Else. Now else block. Now we can compute. Here we return GCD again. Return. We call GCD again. I will say T will be GCD. I will say T, just int G equals, we are calling this function again, GCD A, no, we should call B, right? B. This is remainder B, R, X, Y. So we are recursively calling this function again. Then at this point, we are computing Q, int, Q equals Q equals A over B minus. Please don't forget this. Here, don't forget this. Then at this stage, if x is 0, base root, okay, base root 0, x equals 0, if x equals 0, then x equals 0 means this state, initial state. We should set x equals 1, y equals q, then we repeat. Then it's done. Okay? Then else statement, else, here, tmp, int, t equals x equals y, then y equals x plus y times q. Q is executed here, computed here. Then else statement, else block closes. Now here, now before closing, this is if statement return, else statement should return here. Return this G. This is GCD G. So this is basically, now we close once again here. It closes this. Now we close function. This is Euclidean algorithm using recursive function call. If you are not accustomed to recursive function call, it might be a bit challenging, but I hope you understand. You try it several times, then you can understand what it means. So before I close this session, I need to mention one thing. Please watch these preconditions. Precondition. For example, if we are passing functions like 15x, then 56y equals GCD 56, no, 15, 56. This does not work. This does not work because A is less than B. So this is a recursive function call. It does not work. So we create another function here. For example, int compute CMP GCD. I will say like this: A, B, C, X, Y, like this. Then here I will say this is underbar. This is hidden functions. I will say just say int GCD, int A, int B, int X, int Y. Here in this function we are calling if b greater than a, swap AB, right? We call like this. Then here int G is greatest common divisor, underscore GCD A, B, X, Y. Good? So at this point we call this function and get GCD and XY. At this point we got XY. Please note that in this function we swapped A and B. So we don't know if this X value belongs to this one or this one. We don't know because we swapped. In some cases we swapped, in other cases we haven't. So we need here to properly handle that. We have to apply this equation. So if say A times X plus B times Y equals G. You understand? Means if this equation holds, no, not G. Not not equal G. This is G. Then we have to swap x, y. This is very important, right? This is very important. So then we end. Then we return G. So this is internal routine. This is the internal underscore underbar like this, underbar. This is external public interface. This is hidden interface. You have to make, in case of we are losing loop, we can put it inside the loop, function of the loop. But if we are going to use recursively, then this is the way to choose how to implement it. Now I am going to move my desktop and I will show you how to implement this. So in this equation, the result of this will solve these equations. Here x, y. And I move to my desktop, my laptop computer, then I will implement it and I will show you, I will share the code with you. And in my next video, I will show you how to solve things like this. Ax modulo k mod n. Using this equation, after solving this, we can solve this. So in my next video, I will show how to solve this. I will add a solution, a project, new project. I will name it extended Euclidean algorithm. I select empty project. I make it as a starter project. I will add a file, source file. I will name it Euclidean extended Euclidean algorithm. Include IO stream, int main. Now here we are going to solve ax plus by equals gcd ab, like this. Here int, we will first use with loop gcd loop. I will name like this: int b, int x will be reference, int y, here first, if b greater than a, then we swap std swap. To use the swap, we need utility, probably, or you can also add algorithm if you want. Then here, if intr count will have to be static. Here const expr int max count. I will let 100. Then here count will be 0, q will be max count. Here while R equals A modulo B not 0. Then Q count plus plus A over B. You should not forget this minus. Then A equals B, B equals R. At this point, if count equals 0, it means 15x plus 5x 5y equals GCD. 15 5 equals 5. It means R 15 5 is remainder 5, remainder will be 0. So we should let 15 times 0 plus y 5 5 times 1 equal 5. Okay, so x should be 0, y should be 1, then return b. B is GCD. B is GCD at this point. B would be GCD A B. Okay. Else, as I explained in my theory, in my explanation, initially x should be 1, y should be the last element q count minus 1. Yeah, this is the initial statement. Now we are going loop for int I would be count minus 2. I should be greater than or equal to 0 plus I. Now we are doing loop int t would be x equals y. Now y equals x plus y times q I. Now we solve the problem here. Since it returns here, we also return here. Return b. Okay, or we can just put in single place. For example, we remove this, and we can also remove this. Then we can put return b like this. Now, for example, here int a equals 56, b equals 15. Then we are calling this function int x y. Then GCD would be int GCD loop a b x y. Here std cout a b x y GCD GCD, I would say G CD, and there. Let's run it. Crash it. Let's say what's the problem. We swapped max count 0. Oh, we have to decrease like this. What's the problem? We made some mistake. First, y, then y. Then we still have problems. Sorry, I made a mistake here. This is not x. This should be t. I made a mistake here. T. So please note that I fixed this. Then try again. Okay, it works. Then before I close it, it works. But I want to make sure one thing. Here we swapped A and B, so we have to restore it before passing. How we do that? We can do like this. If the value of A and B have been changed here, so we can reserve previous A, int A1, for example. No. I will create A1, A, B1, B, like this. We saved it. We saved original A and B here. So I will change it. B1, A1, B1, like this. Here I have to change all occurrence of A with A1, B with B1, like this. Okay. Here, return B, not B1, return B1. Okay, we change it. A, B, A, B1, and A, and A, B. Okay, before we have to do this, if A times X plus B times B is not GCD. Y is not GCD. GCD would be P1. Then we have to swap STD, swap X, Y. I have to do like this. This step is actually important because we swapped here, we have to restore the order. We have to do this. Now we run them again. Let's run. Okay. Now another thing. we use this is loop. Now we are going to do the same thing using recursive function call int gcd. I would say recursive recursion. I would say like this. I would say recurse underscore again int a, int b, int x, int y, like this. First use int r would be a modulo b. If r equals 0 means x equals 1 and x equals 0, y equals 1, return b, right? I will give you explanation. We are solving 15x plus 5y equals gcd 15 5 equals 5. It means remainder r remainder 15% 5 equals 0. It becomes 0, right? Then to hold this equation we have to be like this. 15 x becomes 0 plus 5 times 1 equals 5. To hold this equation, x should be, this should be times x should be 0, x should be 0 here, y should be 1 to hold this. So we have to set like this. Else means we can calculate, we can recursively call int g would be g underscore gcd recurse. Now we are calling this function again b, and this should be a modulo b. This is r actually. Then x, y. We are calling function like this again. Here we are computing int q. Q would be a b over a. Here don't forget minus symbol here. Now if x equals 0 means it reached at the bottom. We are initializing x equals 1, y equals q. Else we are doing loop here. Else int t equals x, y and x equals y. Uy will be t plus y times q. Okay, now we are returning g. This is recursive function call. Please note that we didn't swap here. We didn't swap a and b. So this is internal representation. So we will make it to complete. I will copy it. Then here, this is external recursion, like this. Then here, if b greater than a, std swap a b. We are swapping int g. Then we call gcd recursive a b x y. Then at this point, if a times x plus b times y is not equal g, means we have to swap order. std swap a and xy. Okay, so you should not forget this step. Then we can return g like this. Now we have done. Now we are calling recursion GCD. I will call it. Okay, I will call it again to check the result. Here we are calling recursion. Recursion. And here std cout using loop. Now using recursion. The result should be the same using recursion. Okay, now let's run. If the results are the same, Ctrl F5. Wow, the values are exactly the same. This is using the loop, this is using recursion. I will modify it a little bit. And here we don't need it. And also here I will put std cout std and there. Here. So let's try it. Wow, beautiful. 4, x is minus 4, y is 15. So this concludes Euclidean extended Euclidean algorithm. Extended Euclidean algorithm. Next session of video. In my next section of video, we will solve problems like this: 17x modulo k mod, for example, 56. We are going to solve equation like this in my next session. If you can download my this sample source code in my website. I will give you the link in the comment section below, and you can download this sample code, and also you can get more information about cryptography in my website. I will give you the link in the comment section below. And if you like my video, please subscribe and give me like button. Thank you for watching.